In the vast silence of space, motion is the only constant. Stars drift like glowing embers across the black sea of the cosmos. Galaxies swirl in luminous spirals, each containing hundreds of billions of suns, each sun with its family of planets spinning endlessly around it. Even the smallest fragments of matter dance to this universal rhythm. Deep inside every atom, electrons whirl in quantized orbits around their nuclei, forever trapped in a ballet choreographed by the laws of physics. Everywhere we look, from the grandest galaxy to the tiniest particle, there is one undeniable truth. Everything is in motion, and everything is spinning. But why? Why does the universe insist on rotation? Why should matter, when it could have simply fallen inward, instead turn and twist as it collapses? Why does an electron possess spin even when it cannot be said to rotate in any physical sense? Why does our own planet turn once every 24 hours, creating the rhythm of day and night that has governed life for billions of years? To understand this, we must confront one of the most profound and beautiful principles in all of science: angular momentum. Angular momentum is the universe's way of keeping a secret. It tells us that once something begins to rotate, it will continue to do so unless a force intervenes. A spinning top slows only because friction steals its energy. A planet orbits the sun because no force exists to stop its motion through the emptiness of space. This is the rule written into the cosmic code. Motion begets motion. Rotation sustains itself. It is as if the universe, from its very first instant, refused to remain still. If we could stand outside the cosmos and look down upon it, we would see rotation everywhere, at every scale. Galaxies rotate like giant wheels of light. Nebulae twist as they give birth to stars. Planets pirouette through the void, some slowly, others with dizzying speed. Even the most massive black holes, those monsters that devour light itself, spin so rapidly that they drag the very fabric of space along with them. Nothing stands perfectly still, not even the vacuum between stars, where fields and particles fluctuate with invisible motion. This endless dance is not chaos, it is structure. Spin is what stabilizes the universe. A spinning star does not collapse into itself because its rotation creates a delicate balance between gravity and momentum. A galaxy maintains its spiral arms through the combined motion of billions of stars orbiting their shared center of mass. Without spin, gravity would pull everything straight inward, compressing the cosmos into a formless point. Rotation is the counterpoint to collapse, the rhythm that allows creation to persist. And yet, this raises a deeper mystery. Where did all this motion begin? If the universe truly emerged from a single explosive birth, as our theories describe, how did that explosion give rise to such organized rotation? The Big Bang, as we imagine it, was a moment of immense expansion, but expansion alone does not imply spin. Something must have seeded those first tiny twirls, those first minute asymmetries that would later grow into the rotation of stars, planets, and galaxies. To uncover the origin of this universal spin, we must journey backward through time to the earliest moments when space, matter, and energy were born. But before we do, let us pause to imagine the immensity of the stage on which this cosmic dance unfolds. Light from distant galaxies takes billions of years to reach our eyes. When we gaze upward, we see not the present, but the past. Snapshots frozen across time, each galaxy still turning long after its light began the journey toward us. Some of those galaxies no longer exist, their light the final whisper of what once was. Yet even now, their ancient rotations continue to shape the gravitational landscape of the universe. If we could slow down time, every spinning object would reveal its history. The Earth's rotation carries the memory of the cloud of gas and dust from which it formed. The sun's spin records the angular momentum of the nebula that collapsed to ignite it. Every atom's spin is a signature from the quantum realm, a reminder that even the smallest entities in existence are never truly at rest. The universe's rotation is not merely movement, it is memory. It is how matter remembers the moment it was set in motion. Angular momentum is thus more than a mechanical property. It is a principle of identity. A star's rotation influences how it shines, how it ages, and how it dies. A planet's spin determines its weather, its magnetic field, and even the possibility of life upon its surface. On the smallest scales, the spin of particles defines the very structure of matter. The entire hierarchy of the cosmos, atoms, planets, stars, galaxies, is unified by this single physical law. To speak of a universe without rotation is to imagine a clock without hands, a melody without rhythm. Motion gives time its meaning. Without it, there would be no orbits to mark the passing of days, no cycles of light and darkness, no pattern to the unfolding of events. Rotation is not just what the universe does, it is what the universe is. Space and time themselves are interwoven with motion, and through their interaction arises everything we perceive as reality. As our understanding of physics deepened through centuries of observation and experiment, scientists began to realize that angular momentum is not merely a consequence of motion, it is a conserved quantity, an eternal ledger kept by the cosmos. Whenever one object slows its rotation, another must speed up to balance the books. This conservation of spin is the reason the universe's total angular momentum never vanishes. It merely changes form, passing from one structure to another, from stars to planets, from atoms to galaxies. Consider the simplest of analogies. When an ice skater pulls her arms close to her body, she spins faster. Her momentum is conserved. The same rule applies when a collapsing cloud of gas forms a star. As the cloud shrinks, its rotation accelerates. This is the same principle that governs the spinning of pulsars, the whirling remains of massive stars that have died in supernova explosions. From human motion to cosmic motion, the law is identical. But conservation alone does not explain the beginning. For something to be conserved, it must first exist. What we seek is not merely the law that governs rotation, but the source of the first spin itself. If angular momentum cannot arise from nothing, then the universe must have contained it from the very beginning. Was it born spinning? Or did the act of creation itself, the sudden emergence of space, time, and matter, generate the primordial rotations that would define the cosmos forever? The answer lies buried in the faint afterglow of the Big Bang, in the patterns of the cosmic microwave background, that whisper of tiny irregularities in the newborn universe. From these minute ripples of density and energy, every structure we know would later form. But these ripples did more than shape matter. They created the seeds of motion. Through them, the universe learned to spin. And so, to understand why everything from electrons to galaxies turns with such elegant persistence, we must follow the trail of rotation all the way back to the moment when the universe itself was born. In that instant of unimaginable heat and density, where quantum fluctuations set the first imbalance in motion, the story of cosmic spin began. To discover the origin of that spin is to glimpse the very mechanism by which chaos became order, by which the void learned to dance. The universe is not still, and it never was. Motion was woven into its first breath. Every orbit, every rotation, every vibration is a note in a symphony that began at the dawn of time. The next step in our journey will take us to that moment, before stars, before galaxies, before even light itself, to witness how the birth of the cosmos became the birth of spin. In the beginning, before there were stars or planets, before there were atoms or light, there was motion waiting to be born. The universe began not as an orderly clockwork, but as a storm of raw energy and possibility. It was an ocean of chaos, expanding faster than comprehension, its temperature beyond any fire ever imagined. And yet within that fire lay the seed of all the cosmic rotations we now observe. It is strange to think that the swirling of galaxies and the spin of electrons both trace their ancestry to that first fraction of a second, when space itself was still learning how to exist. At the dawn of time, the universe expanded in every direction, a uniform blaze of energy stretching outward. But uniformity in physics is never perfect. The quantum realm does not allow stillness or symmetry to remain absolute. Even in the smallest intervals of time, energy fluctuates. Fields rise and fall, particles appear and vanish. These quantum tremors, invisible and inevitable, gave the young universe its first imperfections. Slight differences in density, smaller than 1 part in 100,000, became the first fingerprints of structure. Those tiny variations had enormous consequences. Where the energy density was ever so slightly higher, gravity began to tug just a bit stronger. Matter gathered more densely in those spots, and as it did, the pull of gravity became stronger still. The effect fed upon itself, amplifying the smallest ripples into vast currents of motion. Within those currents, the first hints of rotation appeared. They were not deliberate or directional, merely the byproduct of uneven collapse, but once born, they could never be undone. Here the law of angular momentum entered the stage. In its simplest expression, it says that if a system of particles begins to rotate, it will continue rotating unless an external force changes its state. Nothing in the early universe could stop that spin. There was no friction, no resistance, only the pure interplay of gravity and inertia. And so, as the first clouds of matter collapsed under their own weight, they began to turn. Each collapse intensified the spin, for as the radius of a spinning system decreases, its rotation must accelerate to conserve angular momentum. This is the same reason a figure skater spins faster when she draws her arms inward. Only now the skater is a cloud of hydrogen spanning light years. Thus, the cosmic pattern was established. From chaos emerged coherence. From random fluctuations came rotation. The early universe was not a tranquil expansion, but a turbulent sea filled with vortices of forming structure. Within a few 100 million years, these swirling regions condensed into the first protogalaxies, the embryonic ancestors of the spirals and ellipticals that now fill the night sky. The very act of gravitational collapse created rotation, and once rotation existed, it shaped everything that followed. Yet there is a deeper beauty hidden in this story. The conservation of angular momentum is not just a physical convenience. It is a reflection of the universe's symmetry. The reason spin is preserved is that the laws of physics do not care which way you face. The cosmos looks and behaves the same in every direction. This rotational symmetry is written into the fabric of space and time itself. It is as if nature decreed that turning the universe would not alter its laws, and from that decree came the unbreakable rule that rotation can neither be created nor destroyed, only transferred. From this perspective, every spinning object is a messenger from the past. When a star rotates, it carries the angular momentum of the cloud that birthed it. When that star dies and becomes a white dwarf or a neutron star, its collapse transfers that momentum into new and astonishing speeds. When a planet spins, it inherits the motion of the swirling disk of gas and dust that once orbited its young sun. All of these motions can trace their lineage back through time, to the turbulence of the early universe and to the quantum whispers that preceded it. Imagine watching the universe evolve in reverse, like a film played backward. Galaxies unwind, their spiral arms retracting into smooth clouds of gas. Stars unform, planets dissolve, matter and radiation blend together in a brilliant fog. As we move further back, the fog thickens, the temperature rises, and structure fades until all that remains is a sea of radiation filled with microscopic fluctuations. Beyond that point, as we approach the first instant of creation, the notion of rotation becomes more abstract. Space and time themselves are too entangled to define directions. Yet even here, the principle of angular momentum endures. For wherever there is motion, however chaotic or undefined, there is the potential for spin. In the first second after the Big Bang, the universe underwent inflation, an expansion so rapid that it defies imagination. Distances smaller than a proton stretched to cosmic scales in the blink of an eye. This inflation smoothed most irregularities, but not entirely. Quantum fluctuations were stretched as well, becoming the seeds of all later structure. Those ripples of energy carried with them tiny amounts of angular momentum. When inflation ended and the universe cooled enough for matter to form, those stored imbalances reappeared as vortices in the primordial plasma. The universe, in a sense, remembered its quantum roots through rotation. The early cosmos was filled with these whirlpools. They were not yet galaxies or stars, but they set the stage for everything that would follow. In regions where matter swirled clockwise, gravitational forces would amplify that rotation. In regions swirling counterclockwise, the opposite would occur. Across billions of light years, this interplay created the web-like structure of the cosmos we observe today. Each filament of galaxies, each void between clusters, each spiral arm owes its existence to that ancient turbulence. When astronomers map the large-scale structure of the universe, they find that galaxies are not randomly distributed. They form filaments and walls that twist across space like strands of silk. This cosmic web is the fossil record of primordial motion. It tells us that rotation was not a local accident, but a universal principle, woven into the formation of structure itself. The spin of galaxies today is a continuation of the spin that began in the early universe. And so, the origin of cosmic rotation is both simple and profound. It began with imperfection. Without the slightest asymmetry, there would have been no preferred directions, no collapse, and no spin. The universe would have remained a featureless expansion of uniform radiation. But nature is never perfectly uniform. It is in the tiny imbalances, the small departures from symmetry, that creation finds its foothold. Through these imperfections, the universe learned to move, and through motion, it learned to organize itself. If we could look deep enough into the cosmic microwave background, that faint relic radiation left over from the Big Bang, we would see the fingerprints of this ancient dance. Slight variations in temperature and polarization correspond to regions where the primordial plasma once swirled. They are echoes of the first rotations, frozen in light. Even now, more than 13 billion years later, we can still read them as a cosmic record of how spin was born. From those delicate beginnings, every subsequent act of cosmic formation inherited angular momentum. Galaxies spun faster as they grew, stars turned as they ignited, and planets began to revolve around their suns. The universe did not need to add more spin. It simply redistributed the spin it already possessed. The conservation of angular momentum ensured that the total amount of rotation in the cosmos remained constant, though its form evolved endlessly. Thus, from chaos came order, and from simplicity, complexity. Rotation is the thread that connects the earliest quantum fluctuations to the spiraling galaxies of today. To ask why everything spins is to ask why the universe is not perfectly symmetrical. The answer lies in the marriage of chance and law, the random flicker of quantum uncertainty governed by the strict conservation of angular momentum. Now the stage is set. From the formless energy of the Big Bang emerged the first swirling structures, the seeds of galaxies and stars. Gravity and spin, working together, would sculpt the cosmos into the luminous tapestry we now see. To follow the next step in this evolution, we must watch as these clouds of gas and dust collapse, twist, and ignite, giving birth to the first spinning worlds of light. The universe was young when its first great structures began to take shape. What had once been a smooth ocean of gas was now thick with knots and filaments where gravity ruled. These regions were vast, some stretching millions of light years across, and within them the earliest galaxies were born. The process was violent, yet inevitable. clouds of hydrogen and helium, cooled by expansion, fell together under their own weight. As they did, their uneven mass distributions created tidal forces, twisting and stirring the collapsing material. Spin became inescapable. Imagine a colossal cloud of gas drifting in the newborn cosmos. It is immense beyond imagining, containing enough material to form billions of suns. At first, its particles move randomly, drifting under gravity's slow pull. But because no cloud is perfectly uniform, one side begins to pull slightly harder than the other. Tiny differences in momentum grow with time, creating a slow rotation. This is the beginning of a galaxy's spin. As the cloud collapses, its rotation quickens, its gas flattening into a disk. Within that rotating disk, the first stars begin to form, igniting and filling the darkness with light. Astronomers call this process the tidal torque effect. It explains how galaxies acquire their angular momentum through the gravitational influence of neighboring matter. Each forming structure feels the pull of others around it, and this interplay of attraction and asymmetry imparts a twist. It is a cosmic exchange of torque that determines how fast and in what direction a galaxy will spin. Over billions of years, this simple mechanism has sculpted the grand spirals and elegant ellipses we see through telescopes today. Every galactic rotation is a fossil of those ancient gravitational interactions. Yet even now, galaxies do not spin in isolation. Their motions are part of a grander pattern. Clusters orbiting other clusters, filaments rotating about invisible centers of gravity, dark matter halos spinning like invisible gyroscopes beneath the luminous structures they contain. The entire cosmic web is threaded with rotation, its filaments twisting like strands of a vast whirlpool. The large-scale spin of the universe is not uniform, but it is universal in its presence. Every part of the cosmos contributes to the grand ballet of motion. The scale of these rotations is staggering. The Milky Way completes a single rotation in about 250 million years. Our Sun, riding one of its spiral arms, has circled the galactic center only about 20 times since the Earth was formed. And yet, on human timescales, these motions seem eternal. We live within rotation so constant that we seldom notice it. The Earth turns once each day, orbits the Sun once each year, and together they drift around the galaxy in a path shaped by angular momentum. The very concept of time, days, months, years, arises from spin. Without it, there would be no rhythm to the universe's unfolding. Still, the question lingers like an echo from the beginning. If everything spins, could the universe itself be rotating? The evidence suggests not, at least not in any way we can detect. The cosmic microwave background, that faint afterglow of creation, appears almost perfectly isotropic. It shows no preferred direction, no sign of a cosmic axis. If the universe were spinning, light from opposite sides of the sky would carry subtle differences, a telltale swirl imprinted on the radiation from the Big Bang. Yet, such a pattern has not been found. The cosmos, it seems, is balanced in its expansion. And yet balance does not mean stillness. Even if the universe as a whole does not rotate, the rotation within it remains the rule. From the formation of galaxies to the birth of stars, spin continues to emerge naturally from the laws of motion. The symmetry that forbids a global rotation is the same one that ensures local motion flourishes. Angular momentum, once seeded, never disappears. It transforms, redistributes, and reappears across every scale. The cosmos does not need to spin as a single object. Its rotation is distributed, woven through the very fabric of its structure. Consider the life of a star as a microcosm of this universal pattern. It begins as a swirling cloud of gas drawn inward by gravity. As the cloud contracts, it spins faster, conserving angular momentum. When fusion ignites at its center, the newborn star glows, its surface rotating at speeds of tens of kilometers per second. Over millions of years, stellar winds carry away some of that momentum, slowing its spin, but not erasing it. When the star's fuel runs out and it collapses into a white dwarf, neutron star, or black hole, its rotation accelerates again. A neutron star can spin hundreds of times each second, a relic of the same law that governs galaxies and planets alike. This rhythm of collapse and acceleration is the heartbeat of the universe. It repeats endlessly at every scale. A spinning cloud forms a star. A spinning star gives rise to spinning planets. And when those planets cool, they retain their rotation as silent records of their origin. Every motion we observe is a continuation of the first motions set in place billions of years ago. The conservation of angular momentum is the thread that connects all of time. When we look up at the night sky, the stars seem still, their light frozen in eternity. But this stillness is an illusion. Everything we see is moving, turning, evolving. The Milky Way is spinning, Andromeda is approaching. Clusters of galaxies are twisting around one another, like dancers in a cosmic waltz. Even the space between them is not fixed. It expands, carrying galaxies farther apart while preserving their individual rotations. The universe is a grand paradox. Everything moves, yet the total pattern remains harmonious. In this motion lies a quiet truth. Stillness is an abstraction. It does not exist in nature. Every atom vibrates, every star rotates, every galaxy turns. Motion is the state of being. It is not a disturbance of equilibrium, but the expression of it. The universe does not fall into motion. It is motion. Spin is how existence expresses itself through time. As we trace this principle back through the ages, we begin to see that rotation is not merely a physical process, but a cosmic signature. It defines how matter clumps, how energy flows, how time itself is measured. It bridges the smallest and largest scales, from quantum particles to galactic superclusters. The same equations describe them all, their differences only of magnitude, not of kind. The universe, in its infinite diversity, follows a single rhythm, the conservation of spin. And so, we return to the mystery that began our journey. Why does everything spin? Because motion is not something that happened to the universe after it began. Motion was there from the start. It is the inheritance of creation, preserved in every orbit, every rotation, every quantum spin. The cosmos does not rest, because rest was never an option. The next step in our exploration will take us even further back to the moment when that first motion was born from the furnace of the Big Bang. To understand why everything in existence spins, we must uncover how the universe itself first began to turn, how chaos gave way to rotation, and how the fabric of space learned to dance. Before galaxies turned and before stars blazed into being, the universe existed as a storm of pure energy. There were no atoms, no light, no space as we understand it. Only a boiling sea of quantum fields, each trembling with potential. Time itself had only just begun to tick. In that first instant, the laws that would govern all future motion came into existence. Among them was one of the most profound: the conservation of angular momentum, the law that would ensure that once rotation began, it would never cease. To picture the birth of the universe is to imagine everything compressed into a single point, smaller than a grain of sand. This singularity contained all the energy that would one day form every galaxy, star, planet, and atom. It was a state so dense, so hot, that even the concept of space inside it becomes meaningless. Then, in less than a trillionth of a second, something extraordinary happened. The universe expanded, not into empty space, but into existence itself. This event, known as the Big Bang, was not an explosion in space, but an expansion of space. The distances between points grew faster than light could travel, carrying with them the seeds of everything to come. At first glance, it may seem that such a perfectly symmetrical expansion could not create motion or spin. But the universe was never truly perfect. Quantum mechanics forbids perfect stillness. Even in absolute emptiness, fields fluctuate. These fluctuations were the first wrinkles in creation, the faint irregularities that broke perfect balance and made structure possible. In that primeval instant, the vacuum itself boiled with uncertainty. Tiny variations in energy density appeared and vanished again, their effects magnified by the universe's violent expansion. Within this storm, small patches became ever so slightly denser than others. Gravity, weak but relentless, began to act upon those denser regions. Over millions of years, they grew into the first clouds of matter, and through the smallest of asymmetries, they began to twist. These twists were not deliberate motions, but the natural outcome of imbalance. In a perfectly uniform sea, there is no reason for anything to turn, but introduce the slightest unevenness and motion follows. A region with a little more mass pulls its surroundings unevenly, setting the stage for rotation. As matter condensed under gravity, these tiny differences were amplified. Angular momentum appeared as a shadow of the universe's own imperfections. Physicists have long sought to understand how such simple irregularities could give rise to the immense rotations we see today. The answer lies in the conservation of angular momentum. Once, matter began to collapse and turn, no force could easily stop it. The early cosmos was frictionless, there was no medium to absorb rotation. Thus, every swirl, every eddy of motion, however small, endured. Over time, these infinitesimal spins became the progenitors of galactic motion. The transition from chaos to structure is one of the most remarkable processes in nature. From the randomness of quantum fluctuations arose the pattern of cosmic order. Gravity was the great sculptor, shaping the universe by drawing matter together. But angular momentum was the chisel, carving out the form of galaxies, stars, and planets. Without it, everything would have fallen inward, collapsing into featureless clouds. With it, the universe learned to build. The first few 100,000 years after the Big Bang were dominated by radiation. Matter and light were locked together in a glowing plasma, too hot for atoms to exist. As the universe expanded, it cooled until protons and electrons finally combined to form hydrogen. Light was freed, spreading outward as the cosmic microwave background, the faint radiation we still detect today. This was the moment when the universe became transparent, and from that moment forward, gravity began to gather matter into the first structures. Within those early clouds of gas, spin was destiny. As matter flowed inward, conservation laws forced the rotation to accelerate. The same principle that makes a skater spin faster when drawing in her arms applied on cosmic scales. In the quiet darkness, where no starlight yet shone, immense whirlpools of hydrogen turned slowly under gravity's grip. The first galaxies were not yet visible, but their rotations were already written into the fabric of space. These swirling clouds were the universe's first engines of motion. They did not merely rotate, they transferred their angular momentum to smaller structures forming within them. Pockets of gas condensed into protostars, each inheriting a fraction of its parent cloud's spin. Thus, from the beginning, rotation propagated downward through every level of structure, from the largest clusters to the smallest particles of dust. It is tempting to imagine this cosmic spinning as random, but the pattern was guided by a deeper logic. Where gravity and asymmetry interacted, rotation became inevitable. Where symmetry prevailed, spin could not exist. The act of creation itself broke that symmetry, turning perfect balance into a universe alive with motion. If we could have observed those first turning clouds, we would have seen a universe that was not tranquil but turbulent, filled with expanding light, collapsing matter, and the first glimmers of rotation. This turbulence was not disorder. It was the process by which energy found form, by which stillness became structure. Out of quantum chaos, cosmic order was born, and at its heart was spin. As billions of years passed, the smallest eddies of the early universe grew into vast cosmic whirlpools. The first galaxies ignited, their stars blazing into life within great rotating disks. The universe, once a uniform fog, had become a dance of spirals and spheres, and all of it, every rotation of every object, could trace its lineage back to those first uneven ripples in the newborn cosmos. Even now, when we look into the night sky, the afterglow of that process surrounds us. Every galaxy, every star, every planet carries within it the memory of that primordial twist. The rotation of the universe's first clouds of matter was not a fleeting accident, but the foundation upon which all structure rests. Motion became inheritance, passed from one generation of cosmic creation to the next. The conservation of angular momentum ensured that nothing would ever again be completely still. From that first imbalance, motion cascaded across the ages, shaping the universe into the form we know today. The question that began as a mystery, why everything spins, now reveals itself as a law of nature, written in the very first moments of time. The story of spin is therefore the story of creation itself. It began not with perfection, but with imperfection, not with order, but with chaos. And from that chaos, the universe learned to move. The next stage of that motion would transform clouds into galaxies, and galaxies into the homes of stars. As the universe continued to expand and cool, the first great structures began to form out of the background haze. What had once been a nearly uniform mist of hydrogen and helium now gathered into immense halos of dark matter. Though invisible, this dark matter provided the gravitational scaffolding that shaped the cosmos. Within these unseen halos, ordinary matter, the gas and dust that would become stars, began to collect. It was inside these vast gravitational wells that the story of spin advanced to its next chapter. The early universe was not calm. It was filled with shockwaves, collapsing gas, and tidal forces that tore at the fabric of forming structures. Each region of space experienced a slightly different gravitational pull, depending on the distribution of matter around it. These differences, subtle at first, became the origin of rotation. As neighboring clumps of matter pulled unevenly on one another, they exerted torques, twisting the collapsing halos. This process, known as the tidal torque mechanism, was the key to the universe's first great rotations. When a proto-galactic cloud began to collapse under gravity, it did not fall straight inward. Instead, it spun, ever so slightly at first, then faster as it shrank. The conservation of angular momentum demanded this acceleration. What had once been a slow drift became a graceful whirl. As the gas fell inward, it flattened into a disk, the natural outcome of rotation. These were the embryos of galaxies, the first organized systems in the young cosmos. Inside these rotating disks, another transformation was taking place. As gas cooled, it began to fragment. Within each fragment, gravity took hold again, creating smaller whirlpools of matter. The process repeated itself on smaller and smaller scales, each preserving a fraction of the spin from its parent structure. In time, the densest regions ignited with nuclear fire. The first stars were born, blazing through the darkness and flooding the universe with light for the first time. Even in their birth, these stars carried the memory of rotation. Each one formed from a spinning pocket of gas, and so each began its life turning on its axis. Some rotated slowly, others rapidly, depending on how much angular momentum they inherited. Their rotation determined their fate, how long they would live, how they would burn, and how they would die. Some of these first stars lived short, furious lives, collapsing after only a few million years and exploding as supernovae. Others lived longer, spreading heavier elements into space. In both cases, their rotation governed their destiny. The birth of spin was not a one-time event. It was a self-sustaining process, repeating across every level of structure. Galaxies spun as they grew, their stars spinning within them, their planets spinning around those stars. Each act of formation preserved and transformed the angular momentum of what came before. The universe was building a hierarchy of motion. a nested chain of rotations, from the vast spirals of galaxies down to the smallest particles of matter. And yet, even as the cosmos grew more structured, it retained the memory of its chaotic origins. The early tidal interactions that gave galaxies their spin also determined how those galaxies would move relative to one another. Some rotated clockwise, others counterclockwise, depending on the forces that shaped them. Across billions of light years, these spins created subtle alignments, faint correlations that astronomers can still measure today. It is as though the universe still echoes with the direction of its earliest motions. This great cosmic rotation did more than shape the visible universe. It also influenced the invisible one, the web of dark matter that underlies everything. Computer simulations of the early cosmos show that dark matter halos twist and merge in complex ways, their rotations guiding the flow of ordinary matter that follows. The shape of every galaxy, whether spiral or elliptical, reflects the angular momentum of the dark structure beneath it. Even in what we cannot see, rotation reigns supreme. In this way, spin became the unifying thread between the seen and unseen, between chaos and order. It transformed the universe from a shapeless cloud into a living cosmos filled with pattern and rhythm. From the perspective of physics, this was inevitable, the mathematical consequence of gravity acting upon asymmetry. But from the perspective of awe, it was miraculous. The universe, through the simplest of laws, learned to create complexity. It is humbling to realize that every motion we observe today is a continuation of that first cosmic stirring. The Milky Way spins because the primordial cloud that formed it once twisted under the pull of gravity. The Earth turns because it was born from a disk that rotated around the young sun. The atoms in our bodies contain electrons that spin because the quantum fields that birthed them carry angular momentum as an intrinsic property. We are made, quite literally, from the motion of the universe. The origin of spin, then, was not a single event, but a continuous unfolding. It began with quantum fluctuations and grew through gravitational collapse. It expanded through the birth of galaxies and stars, passing from one form to another without ever being lost. It is a law without exception, a memory that spans all of space and time. And still, the mystery remains. If the first spin came from imbalance, what created the imbalance itself? What broke the perfect symmetry of the newborn universe and set the first motion into play? To answer that, we must look beyond matter and energy, beyond the observable cosmos, into the realm of the quantum vacuum and the geometry of spacetime itself. For perhaps the universe did not begin in perfect symmetry at all. Perhaps rotation was written into its foundation from the very beginning, not as an afterthought, but as a defining trait of existence. This question leads us onward, from the swirling birth of galaxies to the first truly spinning worlds of light, the stars themselves. It is there, in their luminous rotation, that we find the continuation of the cosmic story. The same forces that twisted the universe into motion would now ignite the furnaces of creation, and in their spin, the next chapter of the cosmos would begin. The universe had passed through its first great transformation. From the quantum chaos of its birth, order had emerged. Galaxies were forming, their vast disks spinning slowly in the darkness, their stars flickering to life one by one. Yet this was only the beginning. The motions that shaped the cosmos on these enormous scales were now repeating themselves on smaller ones, creating the first spinning systems within galaxies, the stars, the planets, and everything that would follow. The same principle ruled them all. Whenever matter collapsed under gravity, it began to turn. Even the slightest irregularity in motion would grow as collapse proceeded. A cloud that was only gently rotating would spin ever faster as it shrank, its speed increasing until centrifugal force balanced the inward pull of gravity. Out of this balance came stability, the formation of disks and rings, and the endless continuation of rotation. Angular momentum was not only a law of motion, it was the universe's way of maintaining order amid collapse. But before these stars and planets came to be, the young galaxies themselves underwent a period of turbulence. They were still gathering mass from their surroundings, merging with other proto-galaxies and colliding in violent encounters that would last for hundreds of millions of years. Every collision exchanged angular momentum. When two galaxies merged, their spins could align, oppose, or tilt, depending on how their orbits met. The result of these interactions was diversity. Some galaxies became elegant spirals, others dense ellipsoids, some irregular clouds of stars. All of them carried the memory of the first spin that began with the universe itself. The cosmic web around them grew ever more complex. Streams of matter flowed along filaments of dark energy, twisting as they fell into the deep gravitational wells of galaxies. These flows were not random. They brought with them additional torque, gradually increasing the spin of galactic disks. In this way, rotation was nourished across billions of years. A galaxy's spin was not fixed at birth. It evolved, refined by countless exchanges of angular momentum with its surroundings. The universe was still learning how to move. Meanwhile, within those whirling galaxies, new generations of gas clouds were forming. Each one, drawn together by gravity, mirrored the process that had created the galaxies themselves. The smaller the cloud, the faster it could spin, for the same angular momentum was now concentrated in a tighter space. This scaling of rotation, slow for the vast, fast for the small, became one of the defining features of cosmic structure. The same law that made galaxies turn slowly and gracefully would later make neutron stars spin hundreds of times per second. The first stars born from these clouds burned with a brilliance unlike anything seen since. They were massive, short-lived, and ferocious, fusing hydrogen into heavier elements at astonishing rates. Their rapid rotation stirred their interiors, mixing fresh fuel into their cores and prolonging their luminous lives by a few million years. But rotation was both their blessing and their doom. When they exhausted their fuel, their cores collapsed inward, spinning faster and faster as they shrank. In that collapse, some became neutron stars, spheres only a few kilometers wide, yet spinning hundreds of times each second, while others became black holes, where rotation twisted even the geometry of spacetime. Every act of stellar death continued the transfer of angular momentum. The explosion of a supernova flung rotating debris into space, seeding future generations of stars with the same inherited motion. When new clouds of gas formed from that material, they already contained the memory of their predecessors' spin. The universe was building a rotational ancestry, a lineage of motion stretching back to the dawn of time. Even now, billions of years later, the same process continues. Every new star, every newborn planet, carries a trace of the ancient spin that first appeared in the early cosmos. The universe has never stopped moving, never stopped redistributing its angular momentum from one form to another. The great rotations of galaxies are passed down through the hierarchy of creation, shaping the spin of stars, the tilt of planets, and even the orbits of moons. At its heart, this process is both mechanical and poetic. The conservation of angular momentum may be expressed in equations, yet its consequence is beauty. The symmetry of galaxies, the rhythm of orbits, the continuity of motion that connects all scales of being. What began as randomness became choreography. The chaotic turbulence of the early universe transformed into the cosmic dance we now witness through our telescopes. It is astonishing to realize that this law, simple enough to describe the turning of a wheel, also governs the motion of entire galaxies. It does not matter whether we are speaking of a skater spinning on ice, an electron in an atom, or a galaxy turning in space. The rule is the same. What turns will keep turning, unless acted upon by another force. The universe obeys this principle with unyielding grace. Through this endless preservation of rotation, motion became the very structure of time. The repeated cycles of stars and galaxies are the metronome of the cosmos, measuring eternity through their revolutions. Even in the far future, when most stars have faded and galaxies drift apart into the cold void, rotation will remain. Neutron stars will still spin, black holes will still twist the geometry around them, and particles will still possess intrinsic spin, the eternal echo of the first motion that began everything. Thus, from chaos came cosmos. From formless energy came motion. From motion came structure. And from structure came the spiraling beauty of existence. The universe learned to spin in its infancy and has never forgotten how. Every atom, every world, every star is a dancer in that original waltz. But to understand how this inherited motion continues its transformation, we must look closer at the next step in the cosmic chain, the birth of the first spinning structures within galaxies. For it was here, in the swirling clouds of gas that became the earliest stellar nurseries, that the ancient law of angular momentum gave rise to the blazing hearts of light we call stars. And with that, the story of spin enters a new chapter, one where the turning of galaxies gives way to the birth of the suns themselves. The galaxies of the early universe were not the serene spirals we see today. They were turbulent and raw, great masses of hydrogen and helium swirling in vast halos of dark matter. Gravity was their sculptor, pulling matter inward, shaping clouds that would one day give birth to the first stars. Yet as gravity drew these clouds tighter, another law asserted its power, the conservation of angular momentum. Every contraction, every collapse, every flicker of motion deepened the cosmic spin. Within these young galaxies, enormous clouds of gas collapsed under their own weight. As they did, their random motions transformed into organized rotation. This was not the calm spin of a settled world, but the violent turning of a storm stretching across hundreds of light years. Every molecule of hydrogen and helium was pulled inward, while simultaneously being swept sideways by the growing rotation. The faster the collapse, the faster the spin. Out of these storms came the first disks of matter, the embryos of stars. The forces at play were elegant yet immense. Gravity pulled inward, pressure pushed outward, and rotation kept balance between the two. When the inward fall met the centrifugal barrier, the gas flattened into a rotating disk. At the center, where density peaked, matter compressed until fusion ignited. The first stars blazed to life, their light flooding the darkness that had persisted since the universe's birth. Around each new star, the remaining gas and dust continued to spin, forming rings and spirals that hinted at the worlds yet to come. Each of these protostars was a miracle of physics. They were governed by the same laws that guide the planets and galaxies, yet their scale made them violent beyond comprehension. As they contracted, their rotation intensified until the outer layers spun at tremendous speeds. Magnetic fields twisted through the disks, channeling streams of charged particles into space. Some of these newborn stars released narrow jets of plasma that extended for light years, carrying away excess angular momentum and allowing the core to stabilize. Even in its earliest stages, the cosmos was already regulating its spin, distributing it across the great web of creation. As more stars formed, their light ionized the gas around them, sculpting vast bubbles of brightness that expanded through the galaxies. The gravitational pull of these luminous regions influenced nearby clouds, stirring them into motion and triggering new waves of star formation. Rotation begot rotation. One generation of stars set the stage for the next, each inheriting and redistributing the spin of its ancestors. Over time, these early galaxies grew more ordered. Collisions between them, frequent in the dense young universe, were not random catastrophes, but engines of transformation. When two galaxies collided, their stars often passed by one another untouched, but their gas clouds merged, compressing and swirling into new configurations. Each collision transferred angular momentum, changing both speed and direction of spin. Some galaxies emerged flattened and calm. Others remained irregular and stormy. The diversity of galactic shapes we observe today is the fossil record of those ancient encounters. Yet the process was far from complete. Within the rotating arms of these young galaxies, smaller clouds continued to collapse into new stars, each preserving a fragment of the larger rotational energy. The cosmic hierarchy was taking shape. Galaxies spinning around centers of mass, stars rotating within those galaxies, and soon, planets orbiting around the stars. From the grand to the minute, the pattern repeated endlessly. The first spinning structures of the universe were thus born from a delicate balance of chaos and law. Gravity supplied the pull, turbulence supplied the asymmetry, and angular momentum supplied the rhythm. This triad of forces determined the architecture of everything to come. Without angular momentum, stars would have collapsed directly into black holes. Without turbulence, rotation would never have arisen. Without gravity, nothing would have formed at all. As these processes unfolded, another profound connection began to emerge. The conservation of angular momentum linked the vast scales of galaxies to the tiny scales of atoms. The same mathematical symmetry that governed the turning of stars also governed the intrinsic spin of particles. Nature seemed to speak one language, its dialects differing only in scale. Whether describing the orbit of a planet or the quantum spin of an electron, the equations were reflections of the same universal truth. Motion is eternal. The early cosmos, in all its turbulence, was already a masterpiece of harmony. The spinning galaxies were like notes in a cosmic symphony. Their stars and clusters, the chords that built the melody of existence. And though the universe was still young, its laws were already ancient, immutable, and precise. In this period of the first spinning structures, the universe became truly dynamic. It was no longer a uniform sea of matter, but a living cosmos filled with interacting systems, each turning in response to the others. Every rotation, every orbit, every pulsation was part of a vast feedback loop that preserved balance through motion. The legacy of this age endures. The shapes of galaxies, the spin of stars, even the distribution of matter across the universe are all consequences of these first great rotations. To understand the universe today, its spirals, its disks, its endless dance, is to see the continuation of what began then. The act of spinning became the act of creation. The first spinning structures were not merely objects, they were processes, living, evolving systems that carried within them the essence of cosmic motion. Through them, the universe revealed its preference for balance through motion, for stability through rotation. And as they matured, they laid the groundwork for what would follow, the formation of stars and planets that would inherit and refine this eternal spin. The next step in the cosmic story begins within these rotating disks, where gravity's pull and motion's persistence gave birth to the stars themselves. From their light and their rotation, the cosmos would learn new rhythms. The universe's grand design was just beginning to unfold. Every star that shines in the night sky began as a cloud of gas turning silently in the dark. Gravity drew it inward, and conservation of angular momentum set it spinning faster as it collapsed. This was the same principle that governed the turning of galaxies, now playing out on a smaller, more intimate stage. Each forming star was a miniature reflection of the cosmos itself, a vortex of light born from motion. At the center of a collapsing cloud, pressure and temperature climbed until nuclear fusion began. The moment hydrogen atoms fused into helium, the newborn star ignited. A new sun blazed into existence, a sphere of incandescent plasma held together by gravity and balanced by the outward pressure of fusion. Yet even as it burned, it continued to rotate. Rotation was not an accessory to its creation. It was an inheritance from the cosmic motion that had existed since the beginning. The physics of this process is beautifully simple, yet endlessly powerful. As a collapsing cloud shrinks, its rotation accelerates to conserve angular momentum. A A cloud the size of a light year can condense into a star the size of the Sun, and in doing so, its spin increases by a factor of billions. The same effect can be seen when an ice skater pulls her arms inward and spins faster, but on a cosmic scale, the forces involved are beyond imagining. In the earliest stages of a star's life, this rapid rotation can be extreme. Young stars often spin once every few days, their equators moving at tens of kilometers per second. Over time, as stellar winds blow material away, this speed decreases. The star gradually loses angular momentum, transferring it to the surrounding disk of gas and dust. Yet the overall motion remains conserved. Nothing in the universe truly stops spinning, it only passes its rotation onward. Around each young star, a disk of material forms, a glowing ring of gas, ice, and rock fragments orbiting the stellar equator. Within this protoplanetary disk, countless collisions and accretions begin. Dust grains stick together, forming pebbles, then boulders, then planetesimals. Each carries a tiny share of the star's angular momentum. As these planetesimals collide and merge, they form planets, and those planets inherit both the direction and the rhythm of the rotation from which they were born. This is why most planets orbit in the same direction and lie in nearly the same plane. They are children of the same spinning disk. The entire solar system, every planet, moon, and asteroid, is a fossil of that original rotation. The orbits of Earth, Mars, and Jupiter all trace back to the same moment of cosmic inheritance. The spin of the Sun set the pattern, and everything that followed fell into step. But while the general pattern of rotation is shared, each planet tells its own story. Earth spins once every 24 hours, a period set by the interplay of its formation, its collisions, and the tides raised by its moon. Jupiter, vast and massive, rotates once every 10 hours, its equator racing through space faster than any other planet. Venus, by contrast, spins slowly and in the opposite direction, its day longer than its year. Uranus tilts nearly on its side, rolling as it orbits the Sun. These differences are the fingerprints of history, the echoes of ancient impacts, gravitational interactions, and the chaotic inheritance of angular momentum across billions of years. Even moons bear the mark of spin. Many, like Earth's moon, are tidally locked, always showing the same face to their planet. This happens when rotation and orbital motion synchronize through the exchange of angular momentum. Energy is dissipated, but momentum is preserved, and equilibrium is achieved through eternal motion. Nothing stops, everything adjusts. The principle of angular momentum governs not only the birth of planets, but also the death of stars. When a massive star exhausts its fuel, its core collapses, and its rotation accelerates dramatically. What was once a sphere, millions of kilometers across, can shrink to a city-sized neutron star that spins hundreds of times per second. The fastest known neutron star completes 716 rotations in a single second, a cosmic lighthouse flashing with the precision of a machine. These pulsars are among the most stable rotators in the universe, their spin so constant that scientists use them as natural clocks to measure time itself. When the most massive stars collapse beyond the neutron star stage, they form black holes. And even there, rotation endures. A rotating black hole drags the very fabric of space around with it, twisting space-time into a whirlpool of gravity. This phenomenon, known as frame dragging, reveals that even in death, motion persists. A black hole is not merely an object, it is a spinning distortion of geometry itself. Thus, the story of stars is the story of spin written in light. From their formation to their collapse, rotation defines every stage of their lives. It determines how they shine, how long they live, how they die, and what they leave behind. The Sun itself rotates roughly once every 25 days, slower at its poles and faster at its equator, a differential spin that shapes its magnetic field and drives the 11-year solar cycle of flares and sunspots. Without rotation, the sun would have no magnetic field, and without that field, the planets would be left unshielded from cosmic radiation. Even life on Earth owes its existence to the star's steady spinning rhythm. The cosmic continuity of spin stretches from the scale of galaxies to the scale of atoms. Every rotation in the heavens is a manifestation of the same fundamental principle that governs the smallest particles. Angular momentum is not merely a rule, it is a unifying thread. The same mathematics describes the orbit of the moon and the intrinsic spin of an electron. The universe uses the same pattern everywhere, from the infinite to the infinitesimal. In every sense, stars are the bridges between these scales. They are the engines that transform the universe's raw motion into light and structure. The spinning of a star does more than conserve momentum. It organizes the chaos around it. Through rotation, disks form. Through disks, planets emerge. Through planets, environments stabilize. And upon at least one such world, consciousness arose to ask why everything spins. The story that began in the darkness of the early universe has now reached the dawn of worlds. The same forces that gave galaxies their rotation and stars their light have sculpted the landscapes of planets and moons. The universe, by conserving its motion, has created the conditions for complexity, order, and life. Yet even this is not the end of the story. For just as stars and planets spin, so too do the smallest building blocks of matter. The principle of angular momentum does not stop at the visible world. It continues down into the quantum realm, where spin becomes not a movement through space, but a fundamental property of existence itself. To follow the story further, we must leave behind the blazing furnaces of stars and descend into the invisible. There, in the strange and beautiful world of quantum mechanics, we will find that spin is not only a force of motion, it is the essence of being. The solar system was born from a single swirling cloud of gas and dust. Long before the sun burned, long before Earth formed, a vast nebula drifted in the quiet arm of the Milky Way. It was a ghostly expanse of hydrogen, helium, and heavier elements left behind by earlier generations of stars. For millions of years, it floated in near stillness until gravity began to gather it inward. With that gathering came motion, and with motion came spin. What had once been diffuse and tranquil became a vast rotating disk, the seed of a system that would one day teem with life. At its heart, gravity pulled the gas tighter and tighter. As it contracted, the spin increased, just as it had in the galaxies and stars before it. The same law governed everything, from the scale of the universe to the smallest atom. Conservation of angular momentum demanded that as the cloud shrank, its rotation quickened. The random jostling of particles gave way to a single, unified motion. The cloud flattened, becoming a disk that stretched billions of kilometers across. In the glowing center of this disk, matter piled up until pressure and heat ignited nuclear fusion. The sun was born. Around it, the rest of the disk continued to rotate. Tiny grains of dust collided and stuck together, forming clumps that grew into rocks, then mountains, then worlds. These growing bodies inherited their spin and orbit from the disk that surrounded the young sun. The direction of their motion, the tilt of their orbits, even the rhythm of their rotation, all were written in the flow of the original cloud. The birth of planets was not random. It was guided by the ancient law that everything which turns will keep turning. The alignment of the planets in nearly the same plane is no coincidence. The entire system was once a single rotating sheet of material. This thinness, this shared direction, is the memory of the disk's formation. Every planet orbits the sun in nearly the same direction and plane, like dancers circling a common center. Only a few deviants, like Pluto, wander with tilted paths, reminders that the dance is not perfect, but beautiful in its imperfections. The transfer of angular momentum shaped everything. As the sun ignited, its powerful winds pushed against the inner disk, clearing away lighter gases and driving the formation of rocky worlds close to its warmth. Further out, beyond the frost line where temperatures were low enough for ices to remain solid, larger planets could form, drawing in thick atmospheres of hydrogen and helium. The outer giants, Jupiter, Saturn, Uranus, and Neptune, became spinning colossi, their rotations rapid and their systems of moons miniature versions of the solar system itself. Each of these planets carries its own history of rotation. Jupiter, the largest, spins once every 10 hours, its equator moving faster than any other planet's. Saturn turns nearly as swiftly, its golden rings tracing graceful arcs through space. The ice giants, Uranus and Neptune, roll through their orbits, tilted and strange, their spins relics of long-ago collisions that altered their alignment. Earth spins with steady grace, completing one rotation every 24 hours, while Venus turns backwards so slowly that a single day lasts longer than a year. These variations are not exceptions to the rule of spin, they are the consequences of it. The solar system remembers every impact, every exchange of momentum, every gravitational encounter that shaped it. Even the smallest worlds keep the memory of rotation. Moons orbit their planets, locked by tides into rhythms that mirror their host's motion. Many show the same face to their planet forever, victims of the slow trade between spin and orbit that tides enforce. Angular momentum does not vanish. It moves from rotation to revolution, from the spin of a moon to the orbit of its planet, from the turning of a planet to the motion of its satellites. It is an eternal economy of motion, each body borrowing from and lending to another. As billions of years passed, this great system settled into balance. The planets found their paths, the moons their orbits, the asteroids their belts. Yet beneath this harmony lies ceaseless movement. The Earth's rotation slows by fractions of a second each century as the moon pulls gently on the oceans, stealing a sliver of angular momentum for itself. The moon drifts away by a few centimeters each year, trading Earth's spin for its own distance. The balance shifts slowly but never breaks. The solar system is a clockwork of motion, a perfect demonstration of the conservation of angular momentum on a grand scale. The planets are its gears, the sun its driving engine. Every turn of every world is a continuation of the spin that began before the sun was born. To watch them move is to see the laws of physics made visible, rotation preserving itself across the eons. Yet even here, amid the ordered beauty of the solar system, mystery lingers. Why, for example, does Venus spin backward, or Uranus lie nearly on its side? The answers lie in the violent youth of the system. In its early days, collisions were common. Worlds slammed into one another, merging or shattering, exchanging spin in titanic impacts. A collision between the young Earth and a Mars-sized body likely formed the Moon, transferring angular momentum in a single, cataclysmic event. Venus, perhaps struck by another massive object, had its rotation reversed and slowed. Uranus may have been toppled by a glancing blow that left it rolling like a giant wheel. Each of these scars is written in the rhythm of their rotation, reminders that even chaos serves the law of spin. Through all these transformations, the fundamental pattern remains unchanged. The sun turns, the planets orbit, the moons dance, and every motion is linked. The same principle that guided the collapse of galaxies and stars continues to shape the turning of our own world. The solar system is a monument to the persistence of angular momentum, a living example of the universe's refusal to rest. When we stand on Earth and watch the sun rise, we are not witnessing the motion of the heavens, but the spin of our planet. The stars appear to circle overhead because we are the ones who turn. Every dawn, every sunset, every orbit of the moon is a reminder that we are passengers in a cosmic dance, billions of years in the making. The solar system is not a static place, but a symphony of motion, each world playing its part in the music of the universe. And this harmony, precise yet dynamic, did not end with the birth of planets. It continues down to the smallest scales of nature, where even particles obey the same law, To understand why the universe spins at every level, we must now look deeper, into the quantum realm, where spin itself becomes something far more fundamental than motion. The solar system is a masterpiece of motion. Every world, every moon, every grain of dust within it obeys the same silent choreography that began billions of years ago. Though we see stability when we look at the night sky, this stability is an illusion born of scale. The truth is that everything moves. The planets orbit in slow arcs, their paths shaped by gravity's pull and their history of rotation. Even the smallest fragments of rock within the asteroid belt spin endlessly, carrying within them the same angular memory as the sun itself. If one could watch the solar system in accelerated time, it would resemble a great dance of light and shadow. The planets would trace spirals around the sun, their orbits flexing and twisting as they feel the distant tug of one another. Jupiter's immense gravity would stir the asteroids, sending some towards the inner worlds and casting others into the cold dark beyond Neptune. Saturn's rings would shimmer, their particles colliding and separating, each following the curve of the planet's rotation. The entire system would seem alive, its movements continuous and interdependent, its harmony guided by the unseen hand of angular momentum. The origins of this dance reach deep into the physics of disks. When the solar nebula flattened under rotation, its inner regions moved faster than its outer ones. Friction within the gas transferred angular momentum outward, allowing material near the center to fall inward and feed the growing sun. This process of momentum exchange is one of the universe's great engines of formation. It allows stars to grow while planets take shape from what remains. The same principle can be seen across the cosmos. Wherever gas and gravity coexist, disks form, and within those disks, rotation dictates destiny. The young solar system was chaotic and radiant. The sun's newborn light blasted the inner planets with fierce winds, stripping away much of their early atmospheres. Collisions between forming worlds were frequent and often catastrophic. Entire planets merged or shattered, scattering debris that would later coalesce into moons. Amid this violence, the orbits gradually smoothed, the chaos giving way to the graceful regularity we now see. Yet that order hides a deep truth. Every bit of that calm came from motion. Balance emerged, not from stillness, but from the conservation of spin. Earth's own story is one of rotation refined by time. Its day, now 24 hours long, was once much shorter. In its youth, Earth may have spun once every 6 hours, its equator moving with furious speed. Over billions of years, tidal forces from the moon slowed this spin, trading Earth's rotational energy for the moon's increasing distance. The two remain locked in a gravitational dialogue, their motions intertwined. Each day that passes on Earth, each orbit of the moon, continues this slow exchange. The lengthening of Earth's day and the moon's drift away are not accidents. They are the inevitable arithmetic of angular momentum's conservation. Mars spins at nearly the same rate as Earth, completing one rotation in about 24.5 hours, while Jupiter turns with astonishing speed, dragging storms of hydrogen and helium around its equator in less than half an Earth day. Saturn's rotation gives rise to its powerful magnetic field, and Uranus, tipped on its side, rolls through space in a slow, peculiar rhythm. Neptune's spin drives supersonic winds that howl across its frozen clouds. Each world's rotation sculpts its climate, its storms, its seasons. The weather of planets is written in the language of spin. Rotation also defines the subtle architecture of the solar system's magnetism. The spinning cores of planets generate magnetic fields that stretch far into space, forming invisible shields that deflect solar wind. Earth's magnetic field protects its atmosphere from erosion, preserving the air we breathe and the oceans we depend upon. Without the planet's rotation, this shield would collapse, and life as we know it would vanish. On Jupiter, rotation amplifies magnetism to extremes, creating radiation belts so intense they could destroy a spacecraft in moments. Everywhere we look, motion sustains existence. Even the most delicate phenomena, the shimmering auroras that dance near the poles, the precession of planetary axes, the slow drift of orbits, arise from this fundamental interplay of spin and gravity. The solar system is a living laboratory, where the law of angular momentum manifests in endless variation. Nothing here stands apart from it. Every movement, no matter how small, participates in the ancient equation that has governed the cosmos since its birth. If we could step outside time and watch the solar system's evolution unfold across billions of years, we would see a story of ceaseless transformation. The planets would shift their orbits slightly, the sun's rotation would slow, the moon would drift farther away. The entire structure would expand and thin as the sun ages and loses mass. In the far future, when the sun swells into a red giant, it will cast off its outer layers, transferring the last of its angular momentum to the planets that survive. Even in death, the solar system will conserve its motion, the remnants still orbiting in quiet circles around a dim white dwarf, the final ember of the star that began their dance. The law that governs this cosmic dance is simple, but its implications are endless. The total angular momentum of the solar system is dominated by the motion of the planets, particularly Jupiter. The Sun, though massive, contains only a small fraction of the system's rotation. Its surface turns once every few weeks, while the planets sweep around it in a slow counterpoint lasting years or centuries. The balance between the Sun's spin and the planet's orbits is exact, a testimony to how motion was distributed in the earliest days. Nothing was lost, it merely changed form. Over the eons, the dance of rotation has shaped not just orbits, but alignments. Most planets spin in the same direction they revolve, a relic of the original protoplanetary disk. Yet exceptions reveal the universe's complexity. Venus spins backward, perhaps due to a long-ago collision or the drag of its dense atmosphere. Uranus, rolling sideways, tells of a tilted birth. Mercury, locked in a resonant rhythm, rotates 3 times for every 2 orbits, a balance born from tidal friction with the Sun. Each anomaly is an adaptation, not a violation, of the same principle. Angular momentum is never lost, only redistributed until balance is achieved once more. The harmony of this system is fragile yet eternal. Small gravitational tugs constantly alter the planet's motions, creating resonances that can persist for millions of years. Jupiter and Saturn, in their great orbits, influence one another's rhythm, stabilizing the solar system while shaping its subtle evolution. Even the distant Kuiper Belt objects beyond Neptune follow patterns imprinted by these resonances, proof that the Sun's influence extends to the very edge of its domain. Beyond that edge lies the Oort cloud, a sphere of icy fragments stretching halfway to the nearest stars. Each of its countless objects drifts in slow, lazy orbits that can take millions of years to complete. Yet even there, far from the warmth of the Sun, the law of spin reigns. Every icy body turns, slowly and silently, its motion a whisper of the universe's first rotation. When one of these comets falls inward and passes close to the Sun, its spin changes as sunlight heats its surface and jets of gas burst forth, pushing it slightly off balance. Even these tiny effects obey the same rule that governs galaxies. The scale changes, the principle does not. From the grand to the minute, the solar system is a continuum of motion. The same physics that governs the orbits of planets governs the turning of atoms. The law of angular momentum connects them like a thread woven through space and time. The universe's memory of its first motion is written into every revolution of Earth, every tide, every storm, every heartbeat of its stellar parent. We live within this great dance, though we seldom perceive it. The rising and setting of the sun, the rhythm of the seasons, even the pull of gravity beneath our feet, are all consequences of rotation. To exist on a spinning world is to be part of a cosmic performance older than time itself. As we gaze beyond the solar system, we find the same pattern repeated endlessly. Other stars host planets of their own, each system born from its own swirling disk, each following the same immutable laws. The Milky Way contains hundreds of billions of such systems, each spinning in harmony with the galaxy's own vast rotation. The cosmic dance extends outward without end, from the smallest orbiting dust grain to the spiraling arms of entire galaxies. The dance of the solar system is more than mechanics. It is poetry written in motion. It tells us that order arises from motion, that balance is born from change, and that the universe, in all its complexity, is united by a single rhythm. The next step in this rhythm lies far smaller and far deeper. For even the tiniest particles, those that make up all matter, possess their own kind of spin, a fundamental twist that is not rotation through space, but an intrinsic property of existence itself. To understand why the universe spins, we must now enter that invisible world, where motion becomes identity and spin is the foundation of all reality. In the realm of the very small, the universe behaves in ways that defy ordinary imagination. The vast orbits of planets and the grand rotation of galaxies give way to a different kind of motion, one that cannot be seen, touched, or even directly pictured. Deep within every atom, inside the nuclei that bind protons and neutrons, and within the very particles that form those building blocks, lies a property known as spin. It is not rotation in the classical sense. No particle spins like a planet or turns like a wheel. Yet this hidden form of angular momentum shapes the behavior of all matter and gives structure to everything that exists. The discovery of quantum spin was one of the great triumphs of 20th century physics. When scientists first studied the motion of electrons in atoms, they found something strange. The electrons behaved as if they carried an intrinsic angular momentum, even though nothing visible appeared to rotate. This was not an illusion, but a fundamental truth. The electron possessed an internal property that made it act like a tiny magnet, aligning with or against magnetic fields in discrete steps. This was the birth of the idea of quantum spin, a kind of built-in rotation that belongs not to motion through space, but to the very identity of the particle itself. Spin in the quantum world is a law unto itself. It cannot change continuously like the turning of a wheel. It comes only in fixed amounts, half, 1, 3/2, 2, measured in units of the reduced Planck constant. Particles that have spin in half units, such as electrons, protons, and neutrons, belong to a family known as fermions. These are the particles that make up matter. Those with whole number spin, such as photons and gluons, are called bosons, and they are the carriers of forces. This simple division between half spin and whole spin defines the architecture of the universe. Everything that has substance is built from fermions, and everything that binds them together is carried by bosons. The consequences of this distinction are profound. The behavior of fermions follows a rule known as the Pauli exclusion principle, discovered by Wolfgang Pauli in 1925. It states that no two fermions can occupy the same quantum state at the same time. This rule alone is responsible for the stability of matter. It is why atoms have structure, why electrons arrange themselves in shells around a nucleus, why solids resist compression, and why we can stand upon the ground without falling through it. If electrons did not have spin, or if they were not subject to the exclusion principle, atoms would collapse and the universe would dissolve into a featureless smear of energy. The Pauli exclusion principle is not merely a rule of behavior. It is the reason that complexity exists. Every atom, every molecule, every solid object is built upon this foundation. The order of the periodic table, the colors of elements, the strength of materials, all arise from the way electrons, guided by their intrinsic spin, arrange themselves within atoms. Matter has shape because spin enforces individuality. Without it, everything would be indistinguishable, every particle occupying the same state, every difference erased. Spin gives the universe structure. On the other side of the quantum divide, bosons behave in the opposite way. They are not bound by exclusion. They can occupy the same state, move in perfect harmony, and merge their identities into a single wave. This is the secret of light, the reason lasers can emit beams of pure coherence. It is also the principle behind the strange phenomena of superconductivity and superfluidity, where particles move without resistance, united in collective motion. Spin thus creates two kinds of existence, one that builds form and one that carries force. Matter and energy, solidity and flow, all spring from this duality. To describe spin mathematically, physicists must leave behind the geometry of everyday space and enter the realm of quantum symmetry. A particle's spin determines how it behaves under rotation. Turn a classical object through 360 degrees and it looks the same. But turn an electron through the same angle, and it does not return to its original state. Only after turning it twice, 720 degrees, does it become indistinguishable from where it began. This strange property has no counterpart in ordinary experience. It reveals that the world of the very small is built upon a geometry that is richer and more subtle than the space we inhabit. This geometry is the reason that quantum spin connects so deeply to angular momentum on cosmic scales. Though the mechanism is different, the principle is the same. Symmetry gives rise to conservation. Just as the rotational symmetry of space ensures the conservation of angular momentum for planets and galaxies, the internal symmetries of particles ensure the conservation of spin at the quantum level. The same logic that governs the turning of worlds governs the twist of particles. The universe, from one extreme to another, is a continuum of motion built upon symmetry. Quantum spin also gives birth to magnetism. The alignment of spins in certain materials creates magnetic fields that shape the behavior of matter on every scale. The magnet in a compass, the magnetic field of Earth, and even the magnetic storms of the Sun all trace their origin to the spins of countless electrons moving in coordinated patterns. Spin is the invisible thread that links the microscopic to the macroscopic, the quantum to the cosmic. At its deepest level, spin may be the reason that time itself has direction. The asymmetry between matter and antimatter, the imbalance that allowed the universe to contain more substance than emptiness, could have arisen from the interactions of spinning particles in the early universe. The preference for one kind of spin over another, a minute violation of symmetry known as parity violation, may have tilted the balance toward matter and thus toward the existence of everything we see. The entire visible universe, every star and planet, every living being, may owe its existence to a tiny asymmetry in the way spin behaves. If we could look inside a single particle, we would not find it rotating like a miniature globe. Instead, we would find a pattern of quantum fields vibrating in ways that have no classical analogy. Spin is not motion through space, but an intrinsic twist in the mathematical fabric of those fields. It is a property as fundamental as mass or charge, a built-in feature of reality itself. To remove spin from nature would be to erase identity, to strip matter of its structure, to silence the music of creation. Quantum spin also connects directly to relativity. When Paul Dirac united quantum mechanics with Einstein's theory of special relativity, spin emerged naturally from the equations. The famous Dirac equation predicted not only the existence of spin, but also of antimatter, a mirror form of matter with opposite charge and identical spin magnitude. When matter and antimatter meet, their spins combine and cancel, releasing pure energy in the form of photons. Thus, spin is not merely a static property, but a participant in the dynamic balance between matter, energy, and the void. Even the vacuum of space, seemingly empty, is filled with virtual particles, flickering in and out of existence, each carrying spin. These fluctuations ensure that the universe can never be perfectly still. The vacuum itself is alive with rotation, a sea of microscopic motion that never ceases. From the quantum scale to the galactic, from the tiniest twist of an electron to the vast turn of a galaxy, the universe is unified by one truth: everything moves, and spin is the language of that motion. Spin is not an afterthought of creation. It is the blueprint from which all structure arises. It shapes the periodic table, governs the behavior of stars, defines the stability of matter, and even determines the geometry of spacetime. In a sense, the universe does not merely contain spin. It is spin expressed at every scale, from the infinitesimal to the infinite. And so, as we trace the thread of motion from the quantum to the cosmic, we find that the laws which govern the very small echo those that govern the very large. The electrons spinning within an atom and the galaxy turning in the void are expressions of the same symmetry, the same conservation, the same memory of the universe's first motion. To go deeper still, we must now turn to the stage upon which all of this takes place, the fabric of space-time itself. For even space, when touched by mass and motion, can twist and turn. Gravity, as Einstein revealed, is not a force, but the curvature of space-time, and when matter spins, that curvature itself begins to rotate. The next part of our journey will explore this profound truth, that not only do galaxies and particles spin, but the very geometry of reality can spin as well. The deeper one looks into the quantum realm, the clearer it becomes that spin is not merely a phenomenon within space, it is a fundamental expression of how space itself behaves. Quantum mechanics shows that particles are not small spheres moving through emptiness, but ripples of probability spread across a field. Their spin is not a rotation in the ordinary sense. It is an intrinsic orientation, a quantum compass that determines how the particle interacts with everything else. Every electron, every proton, every neutron carries this hidden axis, an internal arrow that points nowhere in particular, yet defines everything about its behavior. When many particles interact, their spins combine in ways that give rise to the physical properties we can see. In atoms, electrons pair their spins in opposite directions, balancing their magnetic influences. In certain materials, such as iron, the spins of neighboring electrons align in the same direction, producing powerful magnetic fields that can persist for billions of years. These macroscopic effects are echoes of microscopic spin alignment, vast fields of coordinated quantum orientation that extend far beyond individual particles. Spin also governs the mysterious quantum phenomenon known as entanglement. When two particles interact and then separate, their spins can remain linked in such a way that measuring one instantly determines the orientation of the other, no matter how far apart they are. This strange connection, which Einstein once called spooky action at a distance, defies our ordinary notions of locality and time. It suggests that the universe maintains a hidden coherence, a network of relationships that transcends space itself. Through entanglement, spin reveals the unity of the cosmos, a unity that exists not through proximity, but through information. In laboratories, physicists have learned to manipulate spin with extraordinary precision. By applying magnetic fields, they can flip the spins of individual particles, control their alignment, and measure their responses. This control has given birth to technologies that shape modern civilization. The images we see in medical scanners come from the behavior of nuclear spins in magnetic resonance imaging. The data we store in digital memory is written and read through the alignment of electron spins in magnetic materials. Even the emerging field of quantum computing depends on the ability to control and entangle spins, using them as the building blocks of quantum logic. Thus, what began as an abstract property of the smallest scales has become a tool that defines the technological world. The entire digital age rests upon the manipulation of spin, whether through the magnetism of hard drives, the quantum tunneling of transistors, or the delicate superpositions of qubits. Spin is both the foundation of matter and the currency of information. The duality of spin, half integral for matter, integral for energy, also dictates the structure of the forces that bind the universe. The photon, the carrier of light, has a spin of 1, which allows it to mediate electromagnetic forces between charged particles. The graviton, if it exists, would have a spin of 2, corresponding to the curvature of space-time itself. The particles that carry the strong and weak nuclear forces also possess spin, defining how they interact with the matter they govern. Every force, every field, every interaction depends upon spin to express its symmetry and to conserve its balance. The mathematics of this symmetry lies at the heart of modern physics. Theories such as the Standard Model are built upon groups of transformations that describe how particles change when rotated in abstract spaces. These transformations, known as spin-or symmetries, reveal that particles do not simply move within space. They are representations of deeper geometrical principles. Their spin is the way in which they express the universe's underlying invariance. In other words, the existence of spin is not a feature added to reality. It is the signature of reality's consistency under rotation. If we could translate this mathematics into imagery, we might picture every particle as a tiny gyroscope, its axis invisible but real, its direction encoded in the wave function that defines its being. Each spin contributes to the balance of the whole, ensuring that total angular momentum remains constant across all interactions. When two particles collide, their individual spins combine like notes in a chord, creating a sum that preserves harmony. The universe never loses its rhythm, it merely changes its tune. Even vacuum energy, the ever-present background of the cosmos, is filled with spin. Virtual particles appear and vanish in pairs, their spins always balancing to maintain zero total momentum. This constant creation and annihilation, this quantum froth, ensures that even the emptiest region of space is alive with motion. What we call stillness is merely motion too small for us to perceive. At this scale, the classical idea of motion becomes inadequate. In the quantum world, spin is not rotation through time, but orientation within probability. When a particle's spin is measured, it does not reveal a pre-existing direction, but creates one in the act of observation. The particle chooses an alignment relative to the magnetic field or the measuring apparatus, collapsing a cloud of possibilities into a single outcome. Spin is both property and process, a dance of potentialities crystallizing into reality. The deeper we study spin, the more it appears as a bridge between the tangible and the abstract, between what we can measure and what we can only imagine. It is the signature of quantum geometry, the fingerprint of the universe's symmetry. Every rotation, every orbit, every oscillation is an echo of this hidden order, manifesting across scales far beyond our senses. It may even be that consciousness itself, the strange self-awareness that allows the universe to reflect upon its own existence, arises from the subtle organization of spins within the brain. Some researchers have speculated that quantum coherence among spins in neural structures might play a role in cognition. While this remains speculative, it hints at a profound idea that the same principles governing the spin of particles could underlie the emergence of thought. The motion of the cosmos, from galaxies to electrons, may express itself through the motion of mind. In this way, spin is not simply a physical property, but a universal motif. It is the pulse of the cosmos, the turning of existence upon itself. From the quiet order of atomic shells to the vast rotation of galaxies, the same rhythm persists. The smallest rotations mirror the largest, and through their connection, the universe maintains coherence. Yet there is still one realm left to explore, one where spin transcends even the particles it inhabits. For spin not only shapes matter, it shapes the geometry of space-time itself. a massive body that rotates, can twist the very fabric of the universe, dragging space and time around with it. In the next step of this journey, we will witness how the cosmic dance of rotation continues beyond particles and atoms, beyond planets and stars, into the spinning of space-time itself. Spin is the quiet architect of the universe, a subtle order hiding beneath the noise of creation. To grasp its depth is to realize that the cosmos does not merely rotate within space, it rotates as space. Every particle, every field, every vibration of energy carries this internal twist, this intrinsic orientation that ties it to the rest of existence. The more deeply we explore spin, the clearer it becomes that it is not simply one feature among many. It is the blueprint from which all others are drawn. Imagine the universe at its beginning, hot, dense, and chaotic beyond measure. Quantum fields surged with fluctuations, and within those fields, spin already existed. It was not created in time. It was part of the geometry of being itself. The first particles carried spin as naturally as they carried mass and charge, and through their interactions, the universe gained structure. When particles combined to form atoms, when atoms formed molecules, and when molecules assembled into worlds, the pattern of spin persisted. It was the thread that wove continuity through all change. This continuity is more than poetic, it is measurable. When we observe the polarization of light from distant galaxies, we are detecting the orientation of photon spin that has traveled for billions of years without losing coherence. When we map the magnetic fields of stars and planets, we are tracing the combined effects of countless spinning particles acting in concert. When we study the behavior of electrons in superconductors, we see how spin alignment can create flows of current that move without resistance, hinting at a perfection nature rarely achieves elsewhere. The persistence of spin across scales is the universe's most consistent signature. Spin also provides the foundation for one of quantum theory's deepest principles, the link between symmetry and conservation. Noether's theorem, one of the most elegant results in all physics, tells us that every conservation law corresponds to a symmetry of nature. The conservation of energy arises from the symmetry of time, the conservation of momentum from the symmetry of space, and the conservation of angular momentum from the symmetry of rotation. Spin is the quantum expression of this rotational symmetry, the microscopic fingerprint of the universe's refusal to prefer one direction over another. It is not just conserved, it is demanded by the very structure of reality. Through this lens, the universe's coherence becomes a story of symmetry maintained. The great spinning of galaxies and the minute spin of particles are not separate events, but different manifestations of the same law. The mathematics that describes an electron's spin also describes the orbit of a planet, differing only in scale and context. Angular momentum, whether orbital or intrinsic, is the currency of motion that cannot be destroyed, only transferred or transformed. It is the universe's way of remembering its own beginnings. This memory may be far older than even the Big Bang. Some cosmological models suggest that the universe itself could have inherited a net spin from a previous cycle, a remnant of motion carried through collapse and rebirth. If true, then every rotation we observe, every orbit, every axis, every magnetic field is part of a lineage that stretches beyond time. The spin of particles, then, is not just an isolated property, but a relic of the cosmos's ancestral motion, encoded into the quantum fabric at the dawn of existence. Even at the edge of what we can measure, spin refuses to vanish. In the study of black holes, quantum spin determines how matter behaves as it falls towards the event horizon. The rotation of these singularities twists the paths of particles, aligning and amplifying their spins as they spiral inward. This interplay between quantum and gravitational spin is one of the great frontiers of modern physics, where the laws of quantum mechanics and general relativity meet in a struggle for reconciliation. Understanding how spin behaves in such extremes may reveal how the universe unites its smallest and largest truths. The language of spin also bridges physics with philosophy. It reveals that motion and identity are inseparable, that to exist is to move. Stillness, in the deepest sense, is an illusion. Even in apparent rest, every atom vibrates, every field fluctuates, every particle spins. The universe's stillness is a matter of perception, not of fact. Beneath the calm of a quiet night or the solidity of a mountain, the dance of spin continues, unending and unseen. If one could slow the universe down enough to perceive this motion directly, one would see nothing truly static. The particles of matter would whirl and precess like tiny tops, their orientations shifting through quantum states. Light itself would spiral as it traveled, carrying its spin outward in helical waves. Even space, though seemingly passive, would ripple faintly under the influence of rotating masses. Reality would appear as a vast ocean of intertwined rotations, each sustaining the others in perfect conservation. Spin unites opposites. It turns emptiness into energy, chaos into order, and randomness into rhythm. It is the mechanism through which the universe builds complexity from simplicity. The same symmetry that keeps an electron's spin constant allows galaxies to maintain their graceful spirals. The same conservation that governs the rotation of a neutron star ensures that the angular momentum of the entire cosmos remains unchanged. Across 40 orders of magnitude, from the smallest measurable scale to the largest structures in the sky, the same law endures. This realization carries a kind of quiet wonder. The turning of galaxies, the rotation of planets, the motion of atoms, and the invisible spinning of particles are all expressions of one principle. The universe does not forget. The motion that began at its birth persists through every transformation. Each act of creation, each fusion of stars, each collision of particles conserves the same ancient spin. It is the heartbeat of reality, the pulse that connects all that has ever been. To follow that pulse further, we must now look beyond matter entirely. For spin does not belong only to particles or to planets. It also belongs to space itself. When a massive body turns, it drags space-time along with it, bending not only paths, but time itself. The universe's geometry, too, can spin, a truth discovered through Einstein's great theory and confirmed by the precise experiments of modern physics. The next chapter will reveal how this hidden motion of space transforms our understanding of gravity. It will show that spin is not confined to the things within the universe, but extends to the very stage upon which the universe unfolds. The dance of rotation continues, not in the particles of matter this time, but in the very fabric of space-time, where the cosmos itself becomes the dancer. The universe is not merely filled with motion, it is motion. The planets revolve, the stars rotate, the galaxies spin, and even the smallest particles turn with quantum precision. Yet beneath all this motion lies something deeper, something more fundamental. It is not only matter that moves through space, it is space itself that can twist and turn. Einstein's general theory of relativity revealed that what we call gravity is not a force pulling at a distance, but the curvature of space-time caused by mass and energy. And when that mass spins, it does more than curve space-time. It drags it along, setting the very geometry of reality into rotation. To understand how space can spin, one must first abandon the classical picture of emptiness. In Newton's universe, space and time were absolute, rigid backdrops against which events unfolded. But Einstein's universe is flexible, alive, and dynamic. Space and time are not separate entities. They are woven together into a single fabric called space-time. Massive bodies stretch this fabric, creating the warps and curves we experience as gravity. And when a body rotates, that curvature begins to swirl. The spinning mass pulls space-time around with it, like a spoon stirring thick honey. This effect, known as frame dragging, was first predicted in the early 20th century by Austrian physicists Joseph Lenz and Hans Thirring. They calculated that a rotating planet or star would twist the space around it ever so slightly, changing the paths of nearby objects. For decades, this idea remained theoretical, a subtle consequence of relativity that seemed impossible to detect. But in time, technology caught up with imagination. In 2011, an experiment called Gravity Probe B confirmed that Earth does indeed drag space-time as it spins. The satellite carried 4 gyroscopes so precise that their spin axes could detect shifts of a few thousandths of a degree over the course of a year. As Earth rotated beneath them, the gyroscope's orientations slowly changed, exactly as Einstein's theory predicted. The fabric of space-time was not still. It was turning with the planet. Though the effect around Earth is tiny, it becomes profound near more massive and rapidly spinning objects. Around a rotating black hole, the dragging of space-time is so extreme that nothing can remain stationary. Even light, the fastest entity in the universe, is caught in the whirl. In the region surrounding such a black hole, the ergosphere, space itself moves faster than light relative to distant observers. Within this zone, all objects are compelled to rotate in the same direction as the black hole. It is no longer meaningful to ask whether something is moving through space, for space itself is moving. The equations that describe this extraordinary environment form one of the most beautiful solutions in physics, the Kerr metric, discovered by Roy Kerr in 1963. It describes the geometry of a rotating black hole and predicts phenomena that still challenge our intuition. The faster a black hole spins, the more it drags space-time around, creating a vortex that extends far beyond its event horizon. Matter falling into such a system does not simply plunge inward. It spirals, accelerating and heating until it emits torrents of radiation. Some of that matter escapes along the black hole's poles, shooting into space as narrow jets that can stretch for thousands of light years. These jets, among the most powerful structures in the universe, are born from the spin of space-time itself. This rotational distortion of space has consequences that reach beyond black holes. In neutron stars, which are the collapsed remnants of massive suns, frame dragging affects the paths of orbiting matter, shaping their magnetic fields and directing streams of radiation. Even at the scale of galaxies, the distribution of angular momentum may be influenced by how space-time responds to the collective spin of billions of stars. Rotation, it seems, is not confined to matter, but is an inherent feature of the gravitational field itself. At first glance, it might seem strange that space can move. After all, we tend to think of motion as something that happens in space, not to it. But in relativity, there is no fixed reference frame. There is only geometry, curved, twisted, dynamic geometry. What we perceive as gravity or motion is the result of that geometry changing in time. The spin of a massive body alters the very structure of space around it, just as the mass of that body determines how deeply space is curved. The universe is, in this sense, a single, seamless entity where matter and geometry cannot be separated. Einstein himself marveled at this unity. In his equations, there was no distinction between the motion of matter and the motion of space-time. They were two aspects of one reality. The energy and momentum of matter determine how space-time curves, and that curvature tells matter how to move. When matter spins, the curvature also spins. The dance of rotation extends from particles to stars to the geometry that contains them all. To visualize this, imagine a vast whirlpool. The water represents space-time, and the swirling current represents the rotation of a massive object. A pebble dropped near the center will be pulled inward not in a straight line but along a spiraling path. Even if the pebble were to hover in place, the water's motion would carry it around. In this analogy, the pebble is matter, the whirlpool is curved space-time, and the spin of the black hole is the current that drives the flow. The difference, of course, is that in the real universe, the water is not a substance, but the geometry of existence itself. The deeper implication of frame dragging is that motion is never isolated. Every rotation affects the geometry of the universe, however slightly. Earth's spin twists spacetime around it by an almost immeasurable degree. Yet, that twist extends outward indefinitely. The Sun does the same on a larger scale. The galaxy, rotating majestically through space, may generate frame-dragging effects on an even grander level. It is conceivable that the collective spin of the cosmos itself leaves an imprint upon the structure of spacetime, a faint twist in the fabric of the universe that echoes the original motion of creation. Rotation, then, is not merely an activity of matter within the cosmos. It is a property of the cosmos itself. The universe turns because turning is woven into the fabric of its being. Every spinning planet, every orbiting star, every twisting particle participates in this grand motion, and spacetime, rather than resisting, joins the dance. Spacetime spinning around a massive body is not a metaphor. It is a measurable reality, and its influence reaches farther than intuition allows. Near Earth, the effect is almost imperceptible, yet every satellite orbiting the planet moves through a geometry subtly altered by the planet's rotation. The very direction of time, the way clocks tick, the way orbits precess, is bent by this twisting of space-time. Clocks on satellites must account for both the warping of time due to Earth's gravity and the minute dragging caused by its spin. Without these corrections, the global positioning system would drift by kilometers each day. The world's navigation depends on our understanding of spacetime's rotation. But to glimpse the true power of this phenomenon, one must journey far beyond Earth, to the hearts of galaxies, where gravity reigns supreme. There, spinning black holes act as cosmic dynamos. Their rotation stores immense energy, locked in the fabric of spacetime itself. The faster a black hole spins, the more energy its rotation contains. Under the right conditions, that energy can be extracted, not from matter, but from the spinning geometry around it. This process, first described by physicist Roger Penrose, allows particles to gain energy by falling into the ergosphere and escaping again, stealing a fraction of the black hole's rotational momentum. In this way, the spin of spacetime can power entire galaxies, fueling the blazing jets that stretch across intergalactic space. These jets are among the most magnificent phenomena in the universe. Streams of plasma, moving at nearly the speed of light, erupt from the poles of spinning black holes and travel for millions of light years. Observations show that their alignment matches the direction of the black hole's rotation, confirming that they are driven by the twisting of spacetime itself. The particles within these jets spiral along magnetic field lines that are wound tightly by the rotation of the surrounding geometry. Space turns, time stretches, and energy flows outward in a cosmic ballet of unimaginable scale. The behavior of time near a spinning black hole is perhaps the most striking consequence of frame dragging. To an outside observer, a clock orbiting near the black hole appears to slow, its seconds stretching endlessly as it approaches the event horizon. Yet for the traveler falling inward, time feels normal, a reminder that time is not absolute, but relative to the curvature of spacetime. In the vicinity of a rapidly rotating black hole, the very direction of time can be twisted, blending past and future in ways that challenge human comprehension. The equations suggest that under certain conditions, the path of a particle could loop back upon itself through time, following the rotation of spacetime in a closed curve. These closed time-like paths remain theoretical, yet they show how intimately time and rotation are bound. Even outside the extremes of black holes, frame dragging leaves its mark on the universe. The orbits of stars around the centers of galaxies show subtle precessions, small shifts in their paths, caused by the combined rotation of billions of other stars. The gas clouds that feed supermassive black holes swirl into thin, hot disks, their structure shaped by the same dragging of spacetime that governs every smaller system. Everywhere that mass turns, space and time follow. The mathematics behind this phenomenon reveal its unity. with all other forms of angular momentum. The same equations that conserve spin for particles and rotation for planets apply to the geometry of spacetime. Angular momentum is not merely a mechanical quantity, it is a fundamental aspect of the universe's symmetry. Whether expressed through the rotation of an electron or the twisting of spacetime, it arises from the same conservation law, a cosmic rule that motion cannot vanish. To visualize this, imagine standing at the edge of a spinning black hole. You would see space itself flowing around you, dragging everything along. If you tried to resist the flow, you would find it impossible. There is no way to remain still when space itself moves. The boundary of the ergosphere marks the limit where resistance ends and rotation becomes mandatory. Inside, every atom, every photon, every possibility is caught in the whirl of space-time. What happens within such an environment is both violent and exquisite. Matter drawn into a spinning black hole is stretched and heated, releasing radiation that outshines entire galaxies. The disk of accreting material glows with energy, its innermost edge defined by the balance between rotation and gravity. Closer still, magnetic fields twist into colossal funnels, guiding streams of particles outward in perfectly aligned jets. The black hole's spin dictates the direction of these cosmic beacons, which can remain stable for millions of years. The rotation of spacetime becomes the universe's way of broadcasting its power. Even more mysterious is how a black hole retains its spin. When two black holes merge, their individual rotations combine, and the resulting object spins with a rate determined by the geometry of their union. Recent gravitational wave detections have confirmed this, revealing the final spins of black holes born from such collisions. The waves themselves, ripples in spacetime, carry information about rotation. Each event is a cosmic chord, a vibration of the universe's geometry as it adjusts to a new balance of motion. This connection between rotation and gravitational waves brings us closer to understanding how the universe maintains its angular memory. Every black hole merger, every supernova explosion, every spinning star contributes to the ongoing redistribution of angular momentum across the cosmos. The total remains constant, but its form changes endlessly. The same conservation law that preserves the spin of a particle also governs the dance of galaxies. The idea that space-time itself can spin challenges our deepest intuitions. We are accustomed to thinking of motion as something relative, an object moving against a backdrop. But relativity shows that the backdrop is not static. It can flex, twist, and flow. The universe has no fixed stage. It is the stage and the actor at once. When space-time spins, it demonstrates that the cosmos is self-animated, an organism of motion with no boundary between mover and moved. In a sense, the spinning of space-time closes the circle of the universe's story. From the quantum spin of particles to the rotation of black holes, every form of motion finds its echo in the geometry of existence. The law of angular momentum applies not only within the universe, but to the universe itself. The fabric of reality remembers its own turning. The revelation that space-time can spin changes everything about how we perceive motion. What once seemed a passive void becomes an active participant in the dynamics of the cosmos. When matter moves, space bends. When matter spins, space twists. Time itself, inseparable from space, joins this rotation, flowing unevenly through regions of differing curvature. The universe is not a stage where events occur. It is a living fabric whose threads shift, twist, and turn in response to the energy it contains. Around a spinning black hole, this twisting reaches its zenith. A region forms between the outer ergosphere and the event horizon where space and time swap roles. In this zone, the very concept of standing still loses meaning. To remain motionless would require moving faster than light against the drag of spacetime, an impossibility. Instead, all things are swept into motion, compelled to orbit the black hole's axis of rotation. Even light itself is caught in this endless spin. It can still escape if directed outward, but its path is curved, bent into spirals that trace the geometry of the rotating cosmos. This is the heart of Einstein's vision. Mass tells spacetime how to curve, and spacetime tells mass how to move. The addition of spin deepens the dialogue. Rotation tells spacetime how to twist, and that twisting, in turn, dictates how everything nearby must behave. This interplay is not limited to black holes. It exists wherever mass rotates, in stars, in planets, in galaxies, and perhaps in the universe itself. Every turning object leaves behind a subtle distortion, a whisper of motion embedded in geometry. The gravity of a rotating star, for instance, is not perfectly symmetrical. Its equator bulges slightly outward, and its magnetic field winds around its axis like a coiled spring. These asymmetries alter the paths of satellites and influence the formation of nearby planets. On Earth, this same effect determines the shape of our oceans and the drift of our atmosphere. The equatorial bulge caused by Earth's spin affects how gravity varies across latitudes, guiding the slow precession of our planet's axis. Even our seasons, our tides, and our long-term climate cycles are shaped by the geometry of rotating spacetime. At the galactic scale, rotation becomes the architect of structure. The Milky Way, spinning serenely through space, maintains its spiral shape because of angular momentum distributed across hundreds of billions of stars. This rotation resists the inward pull of gravity, holding the galaxy in balance. The motion of dark matter, unseen yet dominant, adds to this balance, preventing the galaxy's collapse. And just as in the case of black holes and stars, the rotation of the galaxy distorts the spacetime around it, though by an amount far too small for our instruments to yet detect. Still, the principle remains. Wherever there is motion, spacetime follows. One might wonder whether this twisting of space-time could extend to the universe as a whole. Could the cosmos itself, in its vastness, be rotating? The idea has fascinated scientists for nearly a century. In 1949, the mathematician Kurt Gödel found a solution to Einstein's equations describing a rotating universe. In Gödel's model, every point in space is dragged along by cosmic rotation, and time becomes a closed loop. A traveler moving far enough in one direction could, in theory, return to their own past. Though this model does not match our observations, the real universe expands uniformly in all directions. It shows that rotation and time are inseparably linked. Modern cosmology, built upon the near-perfect isotropy of the cosmic microwave background, suggests that the universe as a whole does not possess a significant global spin. Yet even here, subtle hints remain. Some measurements of the cosmic background radiation show tiny asymmetries, minute alignments that could reflect a faint echo of ancient rotation. If these hints hold true, then the universe may have inherited a trace of spin from its earliest moments, a primordial twist frozen into the geometry of spacetime since the Big Bang. The notion that spacetime itself can spin brings unity to all forms of motion. From the smallest quantum particle to the largest galactic cluster, rotation is not imposed from outside. It arises from within. The universe does not require a cause for its spinning any more than it requires a cause for its existence. Motion and being are the same. This is perhaps the most profound legacy of Einstein's theory, that the cosmos is self-contained, self-curving, and self-moving. In the presence of rotation, even the passage of time acquires texture. The flow of moments slows in stronger gravitational fields and twists in the presence of spin. A clock near a rotating black hole will not only run slower, but will experience a direction of time that is skewed relative to the rest of the universe. If one could travel close enough to the event horizon and return, one would find that the external universe had aged vastly, while one's own experience had spanned only minutes. Rotation alters not just the shape of space, but the rhythm of time. Spacetime's ability to spin also reveals something deep about the conservation of angular momentum. When a star collapses into a neutron star or a black hole, it cannot shed its rotation entirely. The angular momentum must go somewhere. The star's core spins faster and faster as it contracts, transferring some of its momentum to surrounding space. This is why the most rapidly rotating black holes can reach near the theoretical limit of rotation allowed by relativity. Space itself absorbs the surplus, storing it in the geometry of the rotating field. The universe ensures that nothing is lost, not even motion. All of this points to a grand symmetry. Angular momentum, conserved across all scales, links the tangible and the intangible, matter and space-time. The same principle that keeps a spinning skater balanced preserves the coherence of galaxies and the stability of space-time. This symmetry, this universal law of rotation, suggests that the cosmos itself is not random, but profoundly ordered. When we look at the stars, we see this order reflected back at us. The planets move in their orbits not by chance, but by inheritance. The stars spin because they were born from spinning clouds. The galaxies turn because the universe's first irregularities carried angular momentum into the future. And the geometry of space-time continues the cycle, twisting wherever motion exists. The idea that space itself can spin completes the chain that began with the birth of the universe. From quantum particles to black holes, from atoms to galaxies, every level of reality expresses the same truth. The cosmos was born in motion, and that motion became the shape of existence. To follow this thread to its final conclusion, we must now examine the principle that binds all these phenomena together, the universal law of angular momentum. It is this law, more than any other, that unites the scales of reality and reveals why everything, everywhere, must keep turning. The farther we look into the workings of the universe, the clearer it becomes that motion is not an accident, but a law. It is written into the foundation of existence, a rhythm that nothing escapes. The same principle that keeps an electron spinning within an atom governs the rotation of galaxies across billions of light years. This principle is angular momentum, the cosmic memory that ensures all motion, once begun, endures unless disturbed. Angular momentum is not a quantity that belongs only to mechanics. It is a universal symmetry. Emmy Noether, one of the most brilliant mathematicians in history, revealed that every conservation law arises from a symmetry of nature. The conservation of energy comes from the symmetry of time, the fact that the laws of physics are the same from one moment to the next. The conservation of linear momentum comes from the symmetry of space, that the laws are the same from one place to another. And the conservation of angular momentum comes from rotational symmetry, the truth that the laws of physics do not change no matter how we turn our point of view. From this single symmetry emerges the order of the cosmos. If a figure skater pulls in her arms, she spins faster because her moment of inertia decreases while her angular momentum remains constant. The same rule governs collapsing stars, which spin more rapidly as they shrink, sometimes reaching hundreds of rotations per second. The same law applies to entire galaxies, their disks turning slowly yet steadily, conserving the spin of the primordial clouds from which they formed. Nothing in the universe loses motion. It only redistributes it. Angular momentum also binds the quantum and the cosmic. In atoms, it determines the structure of electron shells. Each electron occupies a distinct state defined by quantized angular momentum, ensuring that atoms have size and shape. In celestial mechanics, angular momentum dictates orbits and stability. The Moon remains bound to Earth because its orbital motion stores the precise amount of angular momentum needed to balance gravity. As tides transfer energy between Earth and the Moon, the total angular momentum of the system remains constant. Earth slows its spin, and the Moon drifts farther away. Conservation is relentless, exact, and eternal. In black holes, angular momentum takes on an almost metaphysical role. A rotating black hole is defined not by what it contains, but by three numbers: its mass, its electric charge, and its spin. These parameters determine everything about it. The spin shapes the event horizon, the ergosphere, and even the way time flows nearby. When two black holes merge, their angular momenta combine, and the resulting object's spin is the final expression of conservation on the grandest possible stage. Even the gravitational waves emitted in the collision carry angular momentum away, rippling through space-time as the universe rebalances itself. On the scale of the cosmos, the same rule maintains coherence. When galaxies interact, their mutual gravities exchange angular momentum, distorting shapes, triggering star formation, and weaving new structures. The vast cosmic web, the scaffolding of the universe, owes its form to the transfer and conservation of angular momentum across billions of years. Each filament of galaxies, each cluster of stars, each planetary system bears the imprint of motions that began in the universe's first seconds. Angular momentum also preserves the arrow of time. In every interaction, while total angular momentum remains constant, the distribution of energy changes irreversibly. Entropy increases, systems evolve, and motion decays into heat. Yet the underlying rotational symmetry endures. The persistence of this symmetry gives time its continuity. The universe may expand and cool, but its fundamental invariances remain unbroken. At its heart, angular momentum represents balance. It is not merely motion, but structured motion, an equilibrium between inertia and velocity, between geometry and energy. To change angular momentum requires an external torque, a twist applied from outside the system. In the absence of such a force, motion persists indefinitely. This persistence explains why celestial bodies continue their ancient orbits, and why the spin of elementary particles has never altered since the dawn of time. The universe has no friction against itself. The law also reveals something beautiful about the nature of understanding. Every conservation principle in physics stems from symmetry, and symmetry is the essence of simplicity. The fact that angular momentum is conserved means the universe values coherence. It does not favor one direction over another, one observer over another, or one moment over another. Its laws are impartial, elegant, and self-consistent. Angular momentum is therefore not just a rule of mechanics, but a statement about reality's fairness. This fairness allows the universe to build complexity. Because angular momentum is conserved, systems can exchange it to create structure. Stars form disks that birth planets. Galaxies interact to form clusters. Even atoms exchange angular momentum through light, allowing energy to move. Each transfer preserves the whole, enabling creation without contradiction. The universe evolves, yet its total motion remains unchanged. In a way, angular momentum is the handwriting of creation. It records the first motions of the cosmos, the ripples that expanded from the primordial chaos. Every spinning particle, every orbiting moon, every turning galaxy carries a portion of that original signature. Through billions of years, through every transformation, that pattern remains untouched. The conservation of angular momentum is the universe's longest memory. If one could look down upon the cosmos from beyond space and time, one might see not stillness, but a vast, intricate dance. Rotations, within rotations, from the tiniest quark to the largest galaxy cluster, all conserving the same total spin. The universe is not a collection of isolated systems. It is a single organism of motion, self-contained and self-consistent. Angular momentum is the thread that keeps it whole. This principle also hints at something deeper. If every scale of reality obeys the same conservation law, then perhaps angular momentum is not merely a property of motion, but of existence itself. The symmetry that protects it may be fundamental to why anything exists at all. Without it, the laws of physics would lose coherence, energy would fail to conserve, and the universe could not sustain stability. Spin, in all its forms, may be the geometric heartbeat of reality, the rhythm through which the universe maintains its unity. Angular momentum, therefore, is more than a law. It is a bridge between the quantum and the cosmic, between motion and stillness, between the birth of the universe and its eternal unfolding. It tells us that the universe is not random chaos but ordered motion, bound by symmetry and sustained by balance. And if every atom, every planet, every star, and every galaxy holds this same rhythm, then perhaps the universe itself does too. For if angular momentum cannot be created or destroyed, if it must be conserved across all scales, then the total spin of the cosmos must either be perfectly balanced or hidden in plain sight, a symmetry so vast that we have not yet recognized it. In this question lies one of the greatest mysteries of all. Does the universe itself spin? If everything within it turns, can the whole be perfectly still? Or is even the totality of existence caught in the same eternal rotation? The answer leads us to the next frontier, the search for cosmic spin, the possibility that the universe, from its first instant, has been turning ever since. The thought that the entire universe might be turning is as ancient as it is bold. Philosophers once imagined the heavens as nested spheres revolving around Earth, each carrying the stars in a divine rotation. Centuries later, science replaced those crystal spheres with the vast, expanding cosmos we know today. Yet one question still lingers. If everything within the universe spins, could the universe itself be spinning too? In 1949, mathematician Kurt Gödel found a startling solution to Einstein's equations that described a rotating universe. In Gödel's cosmos, every particle of spacetime turns around a common axis, and time itself becomes circular. An observer traveling far enough in one direction could, at least in theory, return to their own past. Though mathematically consistent, such a universe conflicts with what we see. No preferred direction, no global axis, no cosmic rotation visible in the sky. The evidence from the cosmic microwave background, the faint afterglow of the Big Bang, tells us that the universe is astonishingly isotropic. The radiation's temperature is nearly the same in all directions, varying by less than 1 part in 100,000. If the universe were spinning as a whole, this pattern would show a distinct swirl or drift. So far, observations show no such trace. And yet, scientists are cautious. The universe is vast beyond comprehension, and our view extends only as far as light has traveled since the beginning. Tiny anomalies in the microwave background, the so-called axis of evil, a subtle alignment of temperature fluctuations, hint that the cosmos might have a faint global orientation. Whether this is evidence of primordial rotation or a coincidence remains uncertain. If the universe did possess a small but finite spin, the consequences would be profound. A rotating cosmos would twist the trajectories of galaxies and influence the flow of time itself. It could even affect the way matter and energy distribute on the largest scales. Some theories suggest that cosmic rotation could connect to dark energy or to a deeper property of spacetime known as torsion, where space itself resists being twisted. Still, most evidence points to a universe that does not spin as a whole. Instead, it carries countless local rotations, galaxies, stars, particles, all conserving angular momentum inherited from quantum fluctuations at the dawn of time. The universe does not need to rotate globally for everything inside it to spin. Each structure turns independently, yet together they maintain the balance of total angular momentum. Perhaps that is the final symmetry. The universe's overall spin cancels out. Every clockwise motion balanced by a counterclockwise one. Every particle mirrored by its opposite. The cosmos may not revolve around a single axis because it revolves around all of them at once. The idea that the universe itself might turn reminds us of how deeply motion defines existence. Whether or not the cosmos has a grand rotation, its contents reveal that spin is everywhere, not as an exception, but as the rule. And if balance is perfect, then even a universe that appears still is only still because every rotation has found its counter. In the end, the question is not whether the universe spins, but whether it could ever stop. Every atom, every star, every galaxy continues to turn, preserving the motion set in the first instant of time. The silence of the night sky hides a storm of rotation, a billion whirlpools of light, all obeying the same ancient law. The universe may not spin as one, yet it has never been still. The cosmos remembers its birth through motion, and that motion never ends. From the first trembling instant of creation to the quiet turning of a distant world, motion has never ceased. The universe was born spinning, and it has never stopped. Every star, every atom, every fragment of light carries a trace of that first motion, passed down from the beginning of time like a heartbeat that never falters. Angular momentum, the silent keeper of cosmic memory, binds all existence together in an unbroken rhythm. The galaxies continue their endless rotations, their spiral arms sweeping through the void with graceful precision. Stars orbit their centers like dancers in a vast celestial waltz. Around them, planets circle faithfully, their own spins giving rise to days and nights, seasons and tides. Even the smallest particles within those worlds turn according to laws written before time began. Nothing in the universe is still. If we could stop every visible motion, every orbit, every vibration, every flicker of light, we would still find spin at the heart of matter itself. Electrons would continue to twist within their invisible fields. Protons and neutrons would keep their internal spins locked in perfect symmetry. Quantum fields would hum with fluctuations, their rotations too swift and too subtle to measure. Stillness, it turns out, is only an illusion born of our limited senses. The conservation of angular momentum ensures that this motion will never fade. As stars collapse, their spin intensifies. As galaxies merge, their rotations combine and endure. When two black holes join, the space around them rings like a drum, releasing gravitational waves that carry spin into the depths of the cosmos. The energy radiates outward, but the balance of motion remains. The universe loses nothing, it merely transforms. Spin gives structure to chaos. It prevents collapse, stabilizes motion, and carves order from disorder. Without it, the universe would have no shape, no balance, no persistence. Atoms would fall in upon themselves, galaxies would dissolve, and time itself might lose direction. Spin, in every sense, is the architecture of being. And so we return to the question that began this journey. Why does everything spin? Perhaps there is no why. Perhaps rotation is not a product of creation, but its essence. The universe exists because it moves, and it moves because existence itself is motion. Every law of nature, from gravity to electromagnetism to quantum mechanics, describes not stillness, but change. To be is to turn. To exist is to move. When we look at the sky, we are seeing time itself in motion. Light born from spinning stars, stretched across billions of years, still carrying the memory of its origin. The faint glow of the cosmic background, older than any galaxy, still whispers of that first expansion when all motion began. Every photon, every atom, every orbit is part of that same eternal current. The universe has no edge, no center, and perhaps no rest. It expands and cools, it folds and twists, it evolves, but always it moves. The same symmetry that preserved angular momentum in the beginning ensures that it will persist until the end, whatever form that end takes. Even if the stars fade and galaxies drift apart, the rotations they set in motion will echo forever in the curvature of spacetime. In the grand silence of the cosmos, spin is the song that never stops playing. It binds the smallest particle to the largest cluster of galaxies, uniting the visible and the invisible in a single cosmic rhythm. Everything spins because the universe was born turning, and in that eternal motion, it remembers what it is. The dance of existence goes on.